We're now going to talk about, and I think this will spill into next week too, we'll talk about rendering. Rendering is, setting symbols, like Lab 3, where you're setting symbology based on how you want attributes to draw in a legend. Excuse me. And this is if you haven't done Lab 3 yet, this lecture will come in very handy for that particular lab. Feature renderer is an abstract class. We talked about abstract classes back on March 2nd. It's a random fact there that has no significance to anything. And if you remember, an abstract class cannot have objects of its own. All the objects are contained on subclass or child classes. And like we've seen a couple times tonight, there's an abstract class here we'll call feature renderer. So there's specific types of feature renderers that define how we draw attributes in our feature class. It's kind of hard to see the difference here. I bolded some, but it doesn't show up. These are specific types of feature renderer. Simple renderer. In Lab 3, you will do simple renderer, unique value renderer, and class breaks renderer. A simple renderer is just like this is a simple renderer, as we'll see in a second. In a simple renderer, every feature in the shapefile is drawn with the same symbol. This is also a simple renderer. And the legend, if you pick categories and unique value, that's a weird color ramp. That's a unique value renderer, where we draw based on just the name of something, like the names of states here. So when you pick categories and unique values here, that corresponds to unique value renderer. If we draw in graduated colors, like seen here, based on a numeric value, such as population density, where red is the lowest, blue is the highest. That's a class breaks renderer, where we draw based on a range of numeric values. So there's the corresponding three main types of renderers. Those three things are what you'll use 95% of the time, and those three are bolded here where you can barely see it. So simple renderer, unique value, class breaks renderer, what I showed you. You can also set up scale-dependent renderers that change as you zoom in or zoom out. You actually can't do that in ArcMap. You can only do that in ArcObjects. Most of what we learn here you could do in ArcMap manually if you wanted to. There's a few things that you can't. So you could actually set up a renderer so your New York is purple, but when you zoom in it turns orange. You can't do that on the interface as easily. A chart renderer lets you draw pie charts, usually used for demographic information or chemical sampling or something like that. There's a bunch of other renderers I don't think we'll get into here. But again, those three that I showed you are the three different types of renderers that you'll use most of the time. The renderer in every section has to have some weirdness associated with it. We've been working with iFeature layer quite a bit already. But to access the renderer, so the renderer on a feature layer defines how it's drawn. When I went in and defined this color scheme for the count for the state layer, that's the renderer object for the layer. It is not found, of course, because it can't be simple. It's found on iFeature layer. It's found on iGeo feature layer. So here's an object model diagram screenshot of geo feature layer with its properties, and there aren't many. And in fact, of these properties, the only one you really typically use is the renderer property. So renderer class, the renderer property on geo feature layer returns an feature renderer object. We haven't worked with that at all yet. We will in the lectures here, and you will on lab 3. So in the example here, and I won't go through a lot of these because, well, we'll discuss them, of course, but it's pretty similar to the lab, so I don't think we need to type them all out. So in this example here, we've done this a million times. Maybe did this earlier tonight. We're grabbing the first feature layer in the table of contents. But now, as I mentioned on this slide, we need geo feature layers. We need to cast the geo feature layer, and then in the next line here, we capture the renderer. So once we have the geo feature layer, we use the property renderer on the geo feature layer variable. So this gives us access to the feature renderer, which I've called pren here. And as I mentioned, this slide just reiterates what I just said. It says this may need to be casted. It probably would be in most cases to geo feature layer to get the renderer. And this snippet of code steps through setting up a simple renderer, a default fill symbol that is assigned to it, and then utilizing the renderer on a polygon. So here we grab our polygon layer. Again, we're assuming it's a polygon layer. In a real application, I want to test that. I've casted geo feature layer, and I've gotten, in this case, so now on the previous slide, we had the parent feature layer. If I go back a number of slides, in the first example we saw that. But now we need to pick which type of renderer. In this example, we want a simple renderer. We're using simple renderer to just define one color for every feature. So a simple renderer, you're not drawing by state names or population. You just want every state to be orange, for example. So I get the renderer of the feature layer, but I assign it to the variable using the iSimple renderer interface. So I do that when I want to assign the renderer such that it's simple, where it's just one symbol. I then, and this is a review now tying together from before break. We did simple lines and simple markers before break. This is a little different. Simple fill symbol is for polygons. So I'm creating a new iSimple fill symbol using the simple fill symbol class. A simple fill symbol is simply just one color for a polygon. You can do more complex polygon symbology, gradations, and so on. We've seen several examples already of using a Microsoft color, and I'm just grabbing the color orange from Microsoft's color table. And I'm setting the fill symbol's color to the orange and the outline width to 2. And now all of this is similar to what we did to the element before break. And now at the end, we take the renderer that we retrieved above from the feature layer and just set its single symbol to PSFS, which is the symbol we declared here. We need to cast it to the parent iSymbol. In the previous example, we redrew the screen. I mentioned this, I think, before spring break. When you're making changes to the legend, and this will make changes to the legend because you're changing how the layer appears in the legend, we need to update contents method on the map document. So this second to last item redraws the legend. The last item redraws the map. And the result is the zip codes are now drawn with a simple renderer. of the color orange. Questions? We're in lab 3. I know some of you have already done lab 3, so you know. You will have a layer of states, and you'll do a simple renderer to draw all the states by one color. You'll do a unique value renderer to draw them by state name, and then you'll do a class breaks renderer to draw by a population value, I think. I can't recall. So these slides will come in very handy for lab 3. The next type of render we'll talk about is the unique value renderer. This is a qualitative legend, as I showed a moment ago, meaning that we're drawing each symbol by a qualitative, not a numeric value. And state name is a perfect example of that. The state names have no numeric value. State name is just used to describe the state by its name. So if you're drawing a qualitative or a category legend like that, we use the class unique value renderer. There are 3 main properties that we'll be dealing with of a unique value renderer. We'll see them all in a second. Value count, which is the number of unique values you'll use. Field, what attribute are we going to draw with? And then this is a little more cumbersome than you would do on the interface. You need to add a symbol for every possible value. So if we go into our states, go back to unique value renderer. It's easy enough in the interface just to click add all values, but unfortunately you have to have a set of code to add each of these one at a time. So in the lab I'll just make you do, we're not going to make you make 50 of them, we'll just do 3. So you would have to add a symbol for the value Alabama, a symbol for the value Alaska, and so on. So in this case, the field is state name, because that's the field in the attribute table we're basing the legend off of. The value count would be 50, or it was 52 for some reason. And each individual value, you would create 52 symbols and 52 values if you were going to do this for every state. Well, I see. Number 51 is District of Columbia, and they have Puerto Rico in here. That's why it's at 52. Let's create a unique value renderer and assign it to a feature class. So this is going to start out the same as the last example. We're going to get the first layer. And this is the same too. We're casting to IGL feature layer so we can get the renderer. But when we create our renderer variable, this is a little different. We're using IUnique value renderer instead of ISimple renderer like we used a moment ago. We do need to also set the property field count. This indicates how many fields that you'll use. The reason you might say, isn't it always 1? And the answer is most of the time. But just to show you why it's not all the time, you can actually set up a unique value renderer with more than 1 field. And the reason why you would do that, say if I add in counties, if I add in counties based on county name, and there's 3,100 some, so we now have a different color. I'm sure some of the colors get reused, but we have a different color for every county based on the field name. Well, Erie County, New York, Pennsylvania, and Ohio are all drawn in the same color because they all have the value Erie. There's a couple other counties too that occur more than once. I think Washington County, trivia night here, occurs in 30 out of 50 states or something like that. So if I wanted to, I could set up unique values, many fields, and draw the values by a combination of name and state name. So every unique occurrence of state name and name together now is used to draw counties. You can see because of that there's quite a few more counties in the list, or values in the list, and you'll see that Erie County, New York, Pennsylvania, and Ohio are drawn with a different color because now they each have a different color in the legend. So you can see here we have Erie County, New York, PA, and Ohio. You see a couple other like MA, S3. Let's look at Washington. It's a very roundabout way of explaining why you field count is next thing. You look at that, just a majority of states actually have a county named Washington. It's kind of interesting. Maybe not. Turn that off. So that's why you have to set a field count property. But now that I've gone through that, it's usually 1. If you did have a multi-field legend, you'd set it to 2. So we set it to 1, then the next line is set field, the method on unique value renderer. 0 means it's the first field, and the field we're going to use is state name. And we can stop there. If you had set up a unique value renderer with multiple fields, you would set field count to 2, then you would have a second line, prend set field 1, and then the next field you would use. We won't go to that level of detail in the course, like I said, so we can move forward with things, but now you're aware of how you might do that if you need to. So now, what's going to make this more coding is we need to set for every state. We're just going to go through a few for the slides, and you'll just have to do a few for the lab. You need to set up a different symbol for every state. So in this example, I've created a symbol called PSFS2. I've shortened that from simple fill symbol, and I've used the color aquamarine, which is probably some sort of blue. So we've created a simple fill symbol object called PSFS2. And then on this next slide, I've created 2 more new simple fill symbols that I call PSFS3 and PSFS4. This is a case you save a lot of typing by copying and pasting. I mean, I certainly did when I set this up, so I would encourage it, but you be careful. A couple people in lab I noticed made the mistake of copying and pasting and not going back. It's a pain to find every P color 3 and make sure it's color 4. Very easy. Yeah, in fact, I did that when I was creating the slides a number more times than what I made. It's still quicker than typing it all over. It's something to be aware of. So PSFS3 is medium red, and I set up a yellow-green color for PSFS4. And this is how we add values to unique value renderer. There's other things beyond. I think we'll talk about near the end of. Yeah, we will near the end of the course. You don't have the background of all the interfaces yet to do this. So right now, with what we know, it's pretty cumbersome. We'd have to add a value for every single occurrence. If I were meaner, you'd have to make 52 different simple fill symbols to do every state and add them 52 times. We're not going to do that. I think for the lab I made you do 3. Near the end of the class, when we talk about queries, you'll see how you could go through a field and generate a list of unique values, and that would be more robust if you wanted to create a code that created random colors for every state. In this case, so what we do, we take the renderer, there's a method add value, and then you give it the name of the value that it's looking for. In this case, the name of the state. You give it what heading it should appear under in the legend. That'll make sense in the result. And then what symbol. We need to cast a symbol to the generic I symbol. It's not looking for the I simple fill symbol, it's looking for the generic parent class I symbol. So we're going to assign Oklahoma the aquamarine color, Kansas the red color, and then the yellow color to Nebraska in the screenshot. So at the end, we set the renderer, similar to what we did in the first example. We cast the I feature renderer, which is the parent. And then the 2 lines to update the legend and redraw the map. So there's the heading that we saw in the previous example, states. You can create a legend with more than one heading if you wanted to, by not assigning these all states. You could split them up by, Midwestern states, Eastern states, and so on if you wanted. Usually a legend has one heading. I created a multi-head for a hydrofracking project a couple months ago where we had a geology legend and they wanted to separate the geologic features by the primary epoch, quaternary, tertiary, and so on. So that was a case where I did have multiple headings. I had all the rocks from one particular eon in a heading called quaternary, one called tertiary. If you're doing geology, those are eras in Earth's history. But normally you would pick just one heading. So that is a unique value legend. Any questions? The trickiest of the 3 is the class breaks renderer. These are cutoff points. So class breaks renderer are based on quantities or numbers, and then we set up breaks, which are cutoff points between values. So if I go back to my ArcMap, instead of drawing these things this way, I choose quantities. We had this drawn like this before. These are breaks. So there's a break at 76 population density, there's a break at 192, and so on. So this is a class breaks renderer with 5 breaks. So some of the common properties of class breaks of the class breaks renderer. We set a break, which is the cutoff point between classes, the upper level of each range. We'll see here how to define manually or use a statistical method, like natural breaks or quantile. We'll talk about that a little right at the end tonight, which is coming up soon. We set a field, just like we did with unique values. This has to be a numeric field for this to work. Remember, a quantitative legend requires a numeric value. We set the number of breaks that are going to be in the legend, and the absolute lowest value we want to. Say if the lowest population is 20, we set a minimum break of 20. So this code will be very similar, or actually the same. We're not doing anything different here than we have already. We're setting up polygon simple fill symbols for polygons, just like we have for simple and unique value renders. In this case, I set up 4 symbols. I'm not sure why I keep starting at 2. The PSFS2 through PSFS5. And because, not getting too much into cartography, but when you have quantitative values, it's preferable to use a ramp of colors, with the darker color indicating more of something. So I chose yellow, orange, red, and purple to represent sort of a gradation of colors. And so, we set There's a slide missing. Well, you'll get it in the lab. There's a slide missing where you set the brakes to these numbers. I'll have to find that. So you set a brake, the lowest brake to 0. We're setting a brake to 250,000, another brake to 1 million, to 10 million. So there'd be 4 brake counts. I know we're that way. And then here we set the 4 symbols. So you would set 4 brakes with the index 0, 1, 2, 3. 250, 1 million, 10 million, and then a higher number. Now we set the corresponding symbols similar to how you set the symbols in unique value renderer. And then we cast by feature renderer just like we did before, and here is our result. With the lowest, in this case we used age 65. People, how many people in every state are aged greater or more than 65 years old? And there's none, I guess, in the yellow category, below 250,000. There's something odd about that. I wouldn't think Wyoming would have that many. There's barely 250,000 people, period, in the whole state. But it must be right. Any questions? We can also use arc objects to pick the ranges for us. Rather than setting your own class breaks numbers, you can use a variety of methods shown here to pick the class breaks for you. So when I go in to ArcMap, to the legend, I click classify, say quantile, we get a very different map. With quantile, it's like a SAT or GRE score. If there's 5 categories, the top 20% have one color, the next 20% have one color, and so on. It's a quantile method. If we change that to equal interval, now the range in numeric values for every class is the same. So each class would have a range of about 1600. And once we do that, it really distorts the map. There must be one, I think it's Washington, D.C. One outlier can really skew a map when you do it this way. Yep, it's Washington, D.C. is so dense, it's just a city. There's no rural areas. So it puts Washington, D.C. in the top category, and all the other states fall into the bottom category with equal interval. Or you can have something like natural breaks, which uses a Jenks algorithm to try and look for natural breaks, hence the name in the data. All 3 of those methods gave us 3 very different looking maps. So the arc objects classes that correspond to those items are shown here. Your defined interval, equal interval, that shouldn't have a space. Quantile, I didn't show. If your data is normally distributed with a bell curve, you can use standard deviation also. I didn't show that one. That's available. All of those, yet again, there's an abstract class that they all inherit from. The abstract class is called classify. So just as before, this also suffers from having way too many interfaces in class. I apologize about that. They could make some of these things simpler. So we grab the layer just as before. It's actually a class breaks renderer still, because we're using a numeric legend. So we create, but this is where it goes different. We create a new variable using iClassify, but we set it to the class that we want. So in this example, we want a quantile legend. So we create a new quantile class object, which is a co-class, and use the iClassify interface. it gets funny here. We cast feature class of that layer into an iTable interface. And then we also create a new table histogram. ArcObject uses a histogram to divide up these values for us. And then we assign the table for the histogram to the attribute table behind the feature class for that layer.
In this, actually, I don't make you do in the lab. This is more.
I think it's good at least to go over this if you want to do it. We then cast iTable histogram to just iHistogram. So we have another object using iHistogram. We need to assign a field, and I actually use here a field and a normalization field. When we do that, the result is actually a ratio.
So if I show that in, let me show that in ArcMap. Let's say my value is age 65 and up. Why not? The numbers that you see here is just the raw totals of people age 65 and up. And you'll notice if I choose, age 20 somethings, like you, the values don't change because these aren't normalized. Choose the African American. It doesn't change a whole lot because we're just looking at raw totals, and the data will be skewed towards the states with the most population, because these states like New York, California, Texas, Florida have so many more people. No matter what demographic breakdown we choose, we're getting more people. As mentioned, if you're from Buffalo, there's a high representation of Polish Americans in Buffalo. Buffalo's known for that. But if you go to the Census Department and you extract people with a Polish ancestry, everyone thinks, oh, Buffalo will have the most of that in New York State. It's not true. Manhattan does. Manhattan's not known for having a Polish influence, but there's so many more people in Manhattan that they have more Polish Americans than Erie County. But if you divide Polish Americans divided by total population, you get a very different picture, because there are a higher proportion of people in Erie County than they are in New York City. So here, if I change African American from, I now normalize it. So instead of just total number of African American population to black divided by pop 2010, now this is a percentage. So now the blue will be states where the percentage is higher than 57%. And there's a value, I'll do quantile. I'll leave it the same just so we don't. And it changed quite a bit. I will do quantile. It changed quite a bit, and you'll see now the states in the southeast dominating the map.
Let's see here, because now we're showing a very different attribute. We're showing the percentage of people in that demographic category.
So that's that. You do that with that norm field and that normalization field.
And so in this case, instead of just drawing everyone above 65 years of age, we divide that by the total population and the total 2,000 percentages. We then define my values and my frequencies, which the histogram will write. The histogram has a method called getHistogram that writes out the values and frequencies to those two variables. Then we go back to the Esri iClassify object, set histogram, and then give the classify object the values and frequencies. And then finally, the iClassify object has a method called classify. Then you tell it how many breaks you want. 4 in this case.
So now
a little redundant, but we have to set up the same fields in the class break renderer. We set them up in the histogram. And again, I'm sorry this is so long and drawn out. It should be a simple thing.
On the class breaks renderer, we need to set up the same parameters, the same fields of rank count. From the classify interface, we can get the class breaks property, and that actually returns an array. We talked about arrays early in the course. So it creates an array of double type numbers, and then I pull from the array and assign those to the class break renderer classes. Just to top this off with one last confusing thing though, if you were the class break renderer had a minimum break and then it starts after that, but the class breaks array doesn't. You set the minimum break with the class breaks array. So the minimum break is the first item in the class breaks array from classify. So the numbers are all off by 1. And then after that long and drawn out thing, now I'm going to set labels using those breaks. So this will get the numbers that I just set. I convert the number to string using 3 decimal places, using N3. And now we're finally done. So there are the values that it chose using the iClassify object in quantile of age 65 and up divided by the total population. So the states in purple have a proportion of people above 65 years of greater than 13.5%. And you get Florida, which is an expected in the upper Midwest, which is like that because the only people left, just like Buffalo. So that's the last slide of this lecture. 9:39. If there's no questions, we will meet back up